8, we are going to look at series and try to pick a test. So we're going to try to go through a triage process of deciding what is the best way to attack the series. On the exam, I will tell you what test to use so that you don't get spiraling and wasting time. But it's a good skill as you're going through the things in Chapter 10, Section 8, to try to do it on your own, because the more you can internalize what the key features are and why you would pick a certain test are super helpful. So the first thing we usually think about when we see a series is the divergence test. So remember that the divergence test can never predict convergence. It can only predict divergence, and it's for the series that are egregiously diverging. Like when we look at the harmonic series is not egregiously diverging because the terms are in fact going to 0, right? Those terms are approaching 0, but the series diverges. So that's not egregiously diverging. Egregiously diverging, things like this, where the terms aren't even going to 0. And so that's what the divergence theorem picks up. Any series where the terms aren't even going to 0. So maybe we don't write it down, but we at least think in our head, oh yeah, are the terms going to 0? If they're not, then we would write it down and say, oh, it diverges by divergence test. So that's usually the quick check. And then we have this group of 4 special series. We've got the geometric series, and geometric series can have a positive or a negative ratio. And remember that a geometric series is of the form, we have this arc form. It's generally written a(r) to the k. And it will converge if the absolute value of r is less than 1, diverge otherwise. Telescoping series, another special one. And so telescoping usually is kind of obvious because you have 2 terms that are being subtracted, and it creates that telescoping effect where there's a bunch of cancellation. Sometimes a telescoping series, though, is not obvious, and it's written where you have to use PFD first. You have like 1 divided by a product of factors, and you have to separate it and make it look more like the traditional look of a telescoping. And then, of course, the P-series. P-series we use a lot. P-series we use a lot. Here, the form of a P-series is 1 over k to the p. So P is standing for power. So that's one way to remember that you're looking at the power. And notice that here we have an exponential expression in the denominator, and it's the base of that exponential function that's changing, that exponential expression, right? That's the k. Whereas with geometric, it's the exponent. So a geometric series looks like an exponential function. A p-series looks like a polynomial function. Right? Polynomial has a base that's changing. Exponential has an exponent that's changing. And of course, make note of the difference. It feels, here less than 1 converges, here greater than 1 converges. And the reason that we have that opposite effect is that with the geometric series, you're in the numerator. With the p-series, you're in the denominator. And then we have the alternating series. That one is pretty obvious. You'll see the switch. Maybe they try to hide the switch with a cosine or a sine function, but you will see a switch most of the time pretty obviously. And if you see an alternating series, go to the alternating series test. The one time you might have an alternating series where you don't have to go to the alternating series test is if you have a geometric series with a negative r value. That is also an alternating series. So if we recognize one of these 4 special series that have names to them, then we're going to go for that. If not, then the next thing is that we look at the summation summand, and we ask, is it integrable or not? Does it have an antiderivative? Does it look like we can integrate it easily? If so, the integral test is a good choice. The ratio test primarily when we see a factorial, we jump immediately to ratio. And similarly, if we see powers of k, we immediately jump to the root test. So those two also tend to be pretty obvious. And then the last thing here is maybe we have a series that's P series-ish or geometric series-ish. Looks sort of like a geometric series, looks sort of like a P series, but it's not. Then we go to a comparison test. And by P series-ish or geometric series-ish, we're thinking, oh, there's something added. Like for a P series, 1 over k to the p, maybe we add or subtract a constant from that. So it's almost a P series, but it's not quite. There's something added or subtracted that modifies it a little bit. Because a P series is this. It's not this with a +1 or a +2. That's not a P series. Same with the geometric series. Geometric series, AR to the k. If there's something added or if there's possibly a whole nother function in there, it's not geometric. So geometric has to be AR to the k. So let's try a few. Let's see if we can use our mad skills to figure out what to do. So number 12. So this is a special series. It's one of those 4 that we name. Geometric series, P series, telescoping, alternating. Those are our 4 that we consider special. What one is this? Geometric. So this is geometric. Geometric, the exponent is changing. That's what's happening here. But this one is not written in geometric form yet. We're going to do a little modification. It's not written in that arc form yet. What are we going to do to write it in arc?
I'm going to take the reciprocal.
So we want the exponent needs to be just k. And so what we can do is think of this. Remember that when you have a multiplication of exponents, you can turn it into a power. So you can rewrite this as 7 to the -2 to the k. Those are equivalent. And then we can take the reciprocal of that base. So we would end up with 1/49 raised to the k power. Is that okay with everyone? So we wanted to have it in this arc form. In other words, the k has to be all by itself up there in the exponent. Here's the r value right there. And what is a in this case? Well, this one starts at 1. A lot of times when we look at the arc form, it starts at 0. When we have it starting at 1, the a is not sitting out in front. But when we have, this is the more traditional way to look at a geometric series where it's in that arc form, k equals 0 to infinity. Then you see the a, you see the r, and you see the k. With the 1, it's a little bit obscured. What is the a here? 1/49. We plug in our initial index value and get that. So that's our a value. How about the r value? Also 1/49. It's whatever is below the k, whatever the base for the k is. So this allows us to find the sum. Now it didn't ask to find the sum here, but if we can find the sum, we will. On the test, I'll ask you to find the sum if it's a geometric series. So the formula for geometric series is a over 1 minus r. So in this particular case, we're going to have 1 divided by 49 over 1 minus 1 divided by 49. And if I multiply everything by 49, we will end up with a sum of 1/48. So that will be the sum of the series. Now, if the series has this r value less than 1, we do want to say at some point that the magnitude of r is less than 1, therefore we have convergence. So that's our reasoning for convergence. And I want to point that out really carefully because regardless of what this R value was, you can always plug it in this formula. Like if R is 2, you could plug in, let's just say both A and R were 2, you can plug it in here and get a number. You would get a negative number, but it would be meaningless. We know that if R was 2, that diverges because we'd be adding 2, and then we multiply by 2 and get 4, then we multiply by 2 and get 8. You know, we'd be dealing with something egregious like that. So at some point here, before we go to the S, we do want to make sure that we are acknowledging that there is convergence because the ratio is less than 1 in magnitude. So this makes sense over here. This S value only makes sense if R is less than 1 in magnitude. So that's our strategy. All right, so some factorials. So what do we think when we see a factorial?
Ratio.
Ratio test. Anytime we have a factorial, we're going ratio. Ratio test is always the best test with factorials. So the ratio test says that we're going to take the limit as k goes to infinity of the absolute value of a sub k plus 1 divided by the absolute value of a sub k. So we're looking at the ratio of consecutive terms. So the only way that works out is if this ratio of consecutive terms has a limit, just like the geometric series, less than 1. The limit of, and we call this R actually kind of like the geometric series. So let me put an R out in front just to, as a kind of cue that, oh yeah, it's going to act like the geometric series. We have an R. So we have to be a little bit careful here with our factorials. So 4k quantity factorial, to find a sub k plus 1, we need to replace that k with a k plus 1. And if we replace this k with a k plus 1, we will end up with 4k plus 4 factorial. So we're replacing this k with k plus 1. And when you multiply that 4 by the quantity k plus 1, the 4 distributes, giving us 4k plus 4. And down in the denominator, replacing that k with k plus 1, we'll have k plus 1 factorial, and all of that is raised to the 4th power. So there's our a sub k plus 1. And because everything is positive, we don't need absolute value bars anymore. So we take the absolute value, but if everything here is positive, it doesn't mean anything. It doesn't change anything. So there's a sub k plus 1. And now we're dividing by a sub k, which means multiply by the reciprocal of a sub k. So multiplying by the reciprocal, we're just going to flip it. So we will have that. So is there any piece, any factor in there that you're not sure about? So next we're going to try to cancel some stuff. So let's rewrite some of these factors. A couple of, the most obvious one to rewrite first is probably down in the denominator here. We can write this k plus 1 factorial as k plus 1 times k factorial. And then each one of these is going to be raised to the 4th power. We would have to distribute that exponent. So k plus 1 factorial is k plus 1 times k factorial. And then we're going to distribute that exponent. This other stuff over here looks like we're probably just going to leave it the same. I'm just realizing, though, that I probably want to give myself a little more space up here. We're going to have some work to do. Maybe I will move this over a smidge. So any question up to this moment? So all we've really done is simplified the lower left denominator. The upper left, yeah, Marcus?
Doing the k plus 1 to factorial, how does that become k plus 1 to the 4 times k factorial?
So we have two things that are happening. When we have the k plus 1 factorial, do you agree that, do you see that this gets turned into that?
No, that's where I'm missing.
Okay. So if we have something like 8 factorial, that's 8 times 7 times 6 all the way down to 1, correct?
Yes.
So couldn't we write this as 8 times 7 factorial?
Oh, okay.
So we did one subtraction and then dropped in the factorial.
Okay.
We could also, if we needed to, which we're about to do kind of in the numerator, we could have done that also. We could have subtracted 1 twice and then dropped in the factorial symbol.
Okay.
Or, so we can go with any of these factorial things, we can go as far as we want with repeated subtraction by 1, and then we can put the factorial symbol in whenever we need it.
Okay.
So that's what we're doing here. We're
Okay.
saying take the first factor, which is k plus 1, and then we subtract 1 from k plus 1 and get k. Now, if we wanted to, we could do the same thing up here. If we had some oddball situation, we could keep going here as well. We could say, oh, well, this is k plus 1 times k times k minus 1 factorial. We can keep subtracting 1 and put in that factorial symbol wherever it's going to make the most sense when we're trying to cancel things. So up here, this kind of gets at what's going to happen up here. So we have 4k plus 4, and then we're going to subtract 1. When we subtract 1 from 4k plus 4, we end up with a 4k plus 3. So 4k plus 3. And if we wanted to, we could drop the factorial in right there, but that's not helping. Like, we can sort of see what our target is, right? This is our target down here. If we can get a factor that is 4k quantity factorial, that would really be nice because it will cancel here. So we're going to subtract again. So we're going to keep subtracting 1 up here in this numerator. So 4k plus 2. All right, we're still not there. And then 4k plus 1. We're getting super close. We're getting there. So 4k plus 1, we don't want to put the factorial there quite yet, but one more subtraction will give us 4k, and that will have a quantity that's factorialed. And that is what we're looking for, because then we can say 4k factorial, those are going to cancel. Make sense? And then we also have some cancellation over here. We have k factorial raised to the 4th power, k factorial raised to the 4th power. So those are going to go away. And that looks like about all that's going to cancel. Any questions on that canceling?
Seems like a lot of work just to cancel one thing.
Right? It's a good thing it wasn't, we didn't have to go any further. It's a lot of writing. Okay, so in the numerator and in the denominator, we have polynomials. Like if you imagine taking that 4k plus 3 and 4k plus 2 and 4k plus 4 and 4k plus 1 and multiplying it all out, it's just a big polynomial. In the denominator, this is just a polynomial too if you were to expand that. And so what we know about polynomials when we're doing limits at infinity, because we're doing a limit at infinity, all we need to do is look at the dominant term of top, dominant term of bottom, and combine them. So the dominant term of the numerator is just going to be these firsts all multiplied together. That's going to give us the highest power of k in the numerator, the leading term. So that's going to be 4 times 4, which is 16. 16 times 4 is 64. 64 times 4 is 256. So we will have 256k raised to the 4th power. And in the denominator, same idea. If we were to expand this all out, it's a polynomial, and the highest power of k is going to be that k term right in front, which will be k to the 4. Well, those guys cancel. K to the 4, K to the 4. So what is the limit as K goes to infinity of this whole thing? 256. Bless you.
Thank you.
So what is our conclusion then? So this is the ratio test, which parallels the geometric series, which tells us that we're going to compare this to 1, and this is greater than 1. Just like the geometric series, in order to have convergence, you need an R value of less than 1. So this tells us that we have divergence. So if R is greater than 1, there is divergence. And it's always nice when you have a conclusion to go back and look and say, well, could I have seen this coming? With these factorials and these weird groupings with parentheses here and a power there, it's not as obvious as most summands. Many summands you can look at and say, oh yeah, the denominator is going to infinity so much faster than the numerator that I expect convergence. Or the numerator is going to infinity so much faster than the denominator, I expect divergence. This one's not quite as obvious because these are not expressions we're used to dealing with. But what it does say is that 4k quantity factorial goes to infinity faster than k factorial to the 4th. What it tells us. But not as intuitive as many of them. Okay, let's try number 19. What kind of series is jumping to mind when you look at 19?
Root test? No.
So there is a power of k, so we might be able to do the root test, but we would have to do some modification first because there's this pesky addition in the exponent and pesky subtraction in that exponent. So root test is one. That's definitely not ruled out instantly for sure. What type of functions are these though?
Exponential?
They're exponentials which correspond to which special series? Which series has the exponent with the variable in it?
P series? No, it's not
P series is like a polynomial. Remember, P series is k to the p.
Geometric?
So geometric series. Yeah, exponential is geometric. Exponential is geometric. And whether we want to go with the root test or whether we want to see if we can use a geometric series argument, regardless, we need to clean this up. This is not okay and that's not okay. We need to do some math to clean that up. And we know how to use the laws of exponents to do that. We can use the laws of exponents in the numerator. We can write this as 3 to the k multiplied by 3 to the 4. In the denominator, we can write this as 5 to the k multiplied by 5 to the negative 2. And then the series starts at 0. One shortcut that a lot of folks will do is just put a 0 right there. Instead of writing k equals 0 to infinity, if you put a 0 there, we know that it means from 0 to infinity. It's an infinite series. You can use that shortcut if you want, especially in intermediate steps. Okay, so let's get the constants cleaned up here. In the numerator, we have a 3 to the 4, so that's 81. So we're going to have an 81 in the numerator. In the denominator, we have a 5 to the negative 2, which is 1 over 25. So that's actually going to turn into a 25 up in the numerator. And then we have our 3 to the k. And in the bottom, we have 5 to the k. That starts at 0, so we could use our shortcut here. And let's keep going. The 81 and the 25 can factor out to the front. And then inside this summation, doesn't this turn into that? We use our laws of exponents. Now it's in the classic form of a geometric series. And I factored the a out to the front. It's in that arc form, starts at 0. So that's the a. When we plug in 0, this all becomes a 1. So that is the a value, whatever 81 times 25 happens to be. So in order for me to know that you know that this is geometric, we're going to say r equals 3/5. So as soon as you pull that r out of thin air, it's like, okay, you're thinking of a common ratio. This is less than 1, so what does that mean?
Convergence.
Converges. So for a geometric series, less than 1 converges. And now if the question just said, does it converge or diverge, we could stop there. Let's go a little further. Because it's geometric, we can, in fact, find the sum. So the sum is going to be a, which is 25 times 81, over 1 minus r. And so this will end up being, still haven't multiplied that out yet, that's 5/5 minus 3/5, which is 2/5. And I think someone's going to have to multiply this out for me. So multiply 125 times 81.
It's 10,125.
10,125. So that will be, thank you, the sum of the series. Everyone agree? Any piece of that? Like the ones that are these special series, there's not a lot of steps, so you want to make sure you don't leave stuff out. Make sure you indicate the R, make sure you indicate your comparison to 1 and your conclusion. Now, what form is 22? It's also a special series. What series is that?
Geometric.
That is also geometric. Right? Geometric is exponential. The k is in the exponent position, so this is an exponential expression. So that is also. Now, it is also, it's not in the classic geometric form. We're not starting at 0, but we can find a and we can find r instantly. What is a? So we plug in that initial index value, and we have an e plus 1 divided by pi. And then r, same, right? R is what, as long as this exponent is isolated in the sense that it's all by itself, it's just k, not 2k, not k plus 1, then r is whatever sits below it. So it's same as a. Okay, so anytime we have a geometric series, we have to compare the ratio to 1. Is that bigger or smaller than 1?
Bigger.
So 2.7 plus 1 is 3.7-ish. Definitely bigger than 3.14. So this is greater than 1. And our conclusion would be divergence, exactly. So as soon as we have a common ratio that's not less than 1, we know for sure that we are getting divergence. Divergence. Go like that and see everything. Yeah.
I just have a quick question on the
course.
one above.
Sure.
On the first slide we were looking at, if the sum n closely relates to a p-series or a geometric series, we use a comparison test. If we thought that closely related a geometric or p-series and we used a comparison test, would we still get a similar answer, or? Well,
here, so the problem here is that we could use a comparison test. What would you compare to?
See, that's why I was not exactly sure.
So we could, the comparison test with a geometric series, the first thing, if you have any extra constants up here, it would make sense if you were going to build a b sub k that you would just cancel those out for your b sub k.
Okay.
So we could definitely say, hey, let's try to do this with a comparison. We're going to compare it to this. Like that makes perfect sense. And does this one converge or diverge?
Converge.
So this has an R value of 3/5, which is less than 1, which tells us that we do have convergence. So would we want to show the a sub k is the original? So that's going to be 3 to the k plus 4 over 5 to the k minus 2. Do we want to show that that's less than or greater than the b sub k? Less than. So we would have to be able to do this for it to all work out,
Oh, okay.
which may or may not. It's not as intuitive to decide. Like when you have a p series, if we do this, let's suppose we have something that's p series-ish, like k cubed plus 1. The b sub k that we would choose is 1 over k cubed. That's going to converge. So this has a p-value of 3, which is bigger than 1, which tells us convergence. Now, does this satisfy the condition? Could we show that this a is smaller than this b? This denominator is bigger than this denominator, and if this denominator is bigger, then this fraction is smaller. So with the p-series comparison, you can really intuitively figure out whether you're going to be able to show the inequality or not. Here, there's just not intuition in here that's going to allow us to make that conclusion, we'd have to do the math
So
here.
is it because the constants are with the exponent?
Yes.
Okay.
Yeah, because the
So
constants
they
are
would
up in
just
the
be down.
exponent. If they were down below on the base instead of up in the exponent, then we could probably develop some intuition.
Okay.
Like this down here is, down at the base level, so we know that we're increasing the denominator by adding that 1, which decreases the fraction. So we certainly could go comparison here. We just have to do the math and see if the inequality works or not. And if it doesn't work, we will go to the limit comparison.
Okay.
Now, given that it's when you get rid of the 4 and the negative 2, in this constant way, at this stage it makes more sense just to treat it as a pure geometric series. But yeah, that's a good intuition though. Up here is, it's not exactly in geometric form here, so considering the comparison test is reasonable. All right, let's take a look at that. So what do we think in a case like this? Isn't the numerator is going to always be positive though, right? So it's not going to alternate because that sign, that sign is wobbling between -1 and 1, and adding 5 offsets any negatives that might come up from the sign. So this is all positive.
P-series?
So P series,
K to the 1/2.
we have a k to the 1/2. So it's not exactly in a p-series form because a formal p-series is 1 divided by k to the p, but this is p-series-ish. So that's exactly what we're going to do. So we're going to choose a b sub k, and we're going to choose b sub k. We have two choices. The sign of k is just wobbling around. We don't want to have that as part of the b sub k. We want to get rid of that wobble. So the natural choice is to choose 5 over square root of k, or we could write that as k to the 1/2. You could even pick 1 over k to the 1/2. Either of those works. You can pick your b sub k to be anything. We want to pick it as closely connected to this as possible. If we just ditch the sign of k, then we would have this, but we could also choose 1 over k to the 1/2. One thing that we've seen is that by leaving this random constant here, that might be beneficial. With the inequality thing, we always have to subtract one thing to the other side, and if we have a 5 here, having a 5 here might be beneficial to cancel out. Because this is going to diverge no matter what. It doesn't matter if it's a 1 or a 5. Right? This the B sub k series will diverge because P is equal to a half, which is less than 1. So let's see what happens. Let's see if the inequality plays out. So we're going to want to show that A sub k is greater than B sub k, greater than diverging diverges. And you can write it as greater than or equal to. It's not going to really matter. The equal to thing rarely comes up. So here's our A sub k. If we can show that it's bigger than B sub k, which is 5 over root k, we got that. Now, do you think we're going to be able to show that this is true? Let's see. So, yeah, let's ask intuition first. What do you think? Are we going to be able to show that that's true?
No, because
Right.
if you cancel out the root of k, then you get 5 plus sine k greater than 5.
So, good. So certainly this is pretty obvious that these just wipe out, right? Those are positive, so you can multiply both sides. And then when you subtract the 5, you end up with, sinc greater than 0. And that's not true, right? Because sine is going to wobble around between -1 and +1. There are values of k that will create negatives. So this is false. So having the 5 didn't help us. We were hoping that it would help with this cancellation. Do you see that it would also not work if we had a 1? Or would it work with a 1?
Should work with the 1, because then you get 4 plus sine k greater
So
than
the
0.
1 would go right here.
Right, you subtract 1 from both sides, you get 4 plus sine k is greater than 0.
So here's what we would end up with. 5 plus sine of k greater than, so there's a 1 right there.
Right, and then you subtract 1 from both sides.
So then, is that true? That that's always going to be greater than -4? That's definitely true.
Yeah.
So actually keeping the 5 in this case didn't help us. The one that we did last week, if we put a 1 instead of I forget what the constant was that we used in that one example, it didn't work. So actually what we're seeing here is that let's not wipe this out though. Let's just say, let's choose B sub k to be 1 over k to the half. So let's not choose this one. So let's not do that. Choose this. We still have the same conclusion here, right? It still diverges. Multiplying by a constant doesn't change anything. So this did not work. So let's just draw our full statement up here just to make sure that we're starting. So 5 plus sine of k divided by root k greater than 5 over root k. Actually 1 over root k, that's our change. That is what we are changing. The k's in the denominator, the root k's, those cancel. So then we have 5 plus sine of k greater than 1. We subtract that. Yeah, that's true. That is true. So therefore, we do get divergence. Yeah, so a lot of times you can just play with your B sub k and make it do what you want it to do. Now our other choice, we could have just gone to the limit comparison test too. If we got down here, it's totally fine to say, oh, the first choice of direct comparison didn't work. I'm just going to go to the limit comparison. Totally fine. That would be legit. All right, let's try another one of these. So this obviously has a similar format. So what do you want to choose for the B sub k? Do we want the 1 or do we want the 3? Can you tell? Let's put the 1 there first and tell me if this B sub k series is going to converge or diverge.
In this case, I don't think it matters.
So-
So you get cosine 5k, so it'd be between 5 and negative 5, right? Wait,
This is
no,
still going to go
never
between
mind.
-1 and 1.
Yeah, never mind.
Yeah, regardless of that whatever that's called, the phase modifier. So what's the p-value for this p-series? 3, it's greater than 1, which tells us that we have convergence. So in our mind, we have to say, okay, can we show that this is less than this? The k cubes are going to cancel. Here, I'll write it out just to... So we're going to want to show that a sub k is smaller or equal to... Again, you could just put less than. You don't need the equal to. So a sub k is this one. So can you see what we want to do here? Is it going to work with the 1? Is it going to work with the 3? What do you think? Obviously, the k to the 3's are going to cancel. Does the 1 work? Does the 3 work? Do they both work? Do neither work?
It works.
Does it work?
Yeah.
If you put a 1 right there, is this less than 1?
Oh, I thought you meant can we solve it? Sorry.
So 1 is not going to create an inequality that works. How about the 3? If we put a 3 here, would it work? That won't work either, will it? Because cosine of whatever wobbles between -1 and 1. So this could be as much as 1 or as small as -1. So this is going to go between 2 and 4, which is not less than 3. So neither of them are going to work, regardless of whether we did the 1 or the 3 over here. Neither works over here. So this is going to be false no matter what. So if we have a case where we can't massage the b sub k to make it do what we want to do, then we could go to limit comparison. Can anyone think of a different b sub k?
What about like some number greater than 3?
How about a number greater than 4?
Greater than 4, sorry.
Yeah, we could do that. That is totally legitimate. We could say, hey, we know multiplying by a constant does not matter. Let's multiply by 8. If we multiply by 8, so we would take this away, put an 8 there. Now, this is true. So that would work. If we make our b sub k 8 over k cubed, still, this is a p series where p is going to be 3 greater than 1, so you have convergence. Multiplying by 8 does not change convergence or divergence. And then we come over here and we put our 8 over k cubed. The k cubes cancel. This over here, the biggest the left side ever is now is 4. That is less than 8. That's true. So now we can conclude that we have this converge, so this will converge. So that's one way. So whenever we get to this place where we're stymied, we can fiddle with b sub k or go to the limit comparison test. Let's do this one with limit comparison just to see how it would play out. So if we went to the limit comparison test, we would take the limit of a sub k as k goes to infinity. And we're going to divide by b sub k, so that means multiply by its reciprocal. So I'm just going to go with the original b sub k that we picked. So this is, let me just write this, make sure you're remembering. It's a sub k over b sub k. So there's the a sub k. That doesn't change. We could pick whatever b sub k we wanted. We had a k, 1 over k cubed, 3 over k. We tried a couple things. Let's just pick the original, see what happens. Let's just see if the limit comparison test is going to give us anything interesting here. Oh, the k cubes cancel. What's that limit?
Infinity.
Nope.
Oh, undefined.
DNE, right? That limit does not exist. So here is the first example that we put on the board where the limit comparison test doesn't actually work. So this could be a little circular. If we tried the 1 over k cubed, the 3 over k cubed, I'm like, oh crap, the direct comparison test's not working. I'm going to limit comparison. And then we go to limit comparison. Limit comparison totally is inconclusive. So then we would know that we have to go back to the b sub k and try to fiddle with it. Most of the time, if the direct comparison doesn't work, the limit comparison will most of the time. But this is one example where it won't work. So just to give you one example where the limit comparison doesn't work, because there's a lot of the examples in the homework, if you go to limit comparison, it just works, just works, just works, just works. So here's the type of problem where it won't work. And it's because that limit doesn't exist. All right. So let's go to these guys. 32. What technique do you think?
Root.
Yeah, we see that power of k on the outside. Power of k on the outside. The kth root of that will just make that power vanish. So that is good. Hold on, I just got something from my son who's up in that crazy. All right, he's alive and he's at the top of this crazy thing. He's doing this ski thing called Shit for Brains today, which tells you everything that a parent doesn't want to know. What are you doing? Shit for Brains? Okay. At least he's at the top now. All right, so the ratio test doesn't work here because we've got powers of k. Ratio only for factorial. Root test is the kth root, so that's going to wipe this out really nicely. So we're going to take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So the root test, you can kind of see right through it. Right? When you take the kth root of the top and the bottom, you end up with k over k plus 2, and the limit of that is 1. So let's see what happens. All right. So we're going to take the kth root of all of that stuff. We're just so excited because the root test just seems like this is going to just make everything so easy. And then we take our limit and get 1. And then we remember that it's like a geometric series. So if it's bigger than 1, it diverges. If it's less than 1, it converges. But if it's equal to 1, it's what? Inconclusive. So we're like, oh, dang, this felt like it was the perfect test. This is inconclusive, though. Oh, shoot. Inconclusive. All right, well, if it's inconclusive, let's try something else. One thing I see when I look at this is that you could turn this into this kind of thing. You could say, oh, well, that's that. And what form, if you think about k going to infinity, what kind of form is it?
Geometric.
Nope. If k goes to infinity, so geometric is when the power changes but not the base.
Power tower?
Right here is more of a power tower. Both are changing. Right? This is the base of the exponential function. That's the exponent of the exponential function. Geometric, the exponent's changing but not the base. So it's not geometric. So it's more like a power tower. Both the base and the exponent are changing. What is the limit of the inside as k goes to infinity? 1. So it's 1 to the infinity, right? It's the indeterminate form, 1 to the infinity. And we've seen that every single time we've had a 1 to the infinity, the limit is not 0. And that's a great question. Can we build a 1 to the infinity indeterminate form that has a limit of 0? That's a good question. Off the top of my head, I would say probably not. So note, so we want to take the limit. So if we do take the limit of this, this is indeterminate. It's 1 to the infinity. And we had a couple of strategies. So remember that we could do something like this. We could, if we could flip this base, we could put it in an E format. All right, we can flip the base by making the exponent -1. Right, that toggles the numerator and denominator. And then we can do our fraction splitting stuff. And we have that shortcut. We have that shortcut that we've looked at a couple of times. What is that limit?
E to the -2.
E to the -2. So that limit is 1 over e squared. That is not equal to 0. We are in one of these egregious divergence situations where the terms aren't even going to 0. So this series is like, who cares what's happening in the front? But when we get way out, it's like we are taking 1 over e squared plus 1 over e squared plus 1 over, out in the tail. That is essentially what's happening. That is going to go to infinity. Right? The only way a series could ever converge, the terms must go to 0. Stockton?
So can if on the test, if we saw that it goes to e to the -2, can we say just that it goes to e to the -2 instead of like showing how it goes, how we would solve it to go?
Yes.
Okay.
So on the test, one of the questions is going to say use the log limit process, and then you have to go through the whole process. But if it's part of a bigger problem, you don't have to actually, you can use our shortcut.
Okay.
So remember, our shortcut says that the limit as k goes to infinity, if we generalize, we're going to have 1 plus a over k to the bk. That equals, bless you, e to the a times b. Yeah. So that's our, so we showed that using the log limit process. So on the test, if this is part of a bigger question, the only time you would have to show how you get to this with the log limit process if it says show using the log limit process. So our conclusion here is that this is not 0, therefore diverge by divergence test. All right. Let's see this one. Immediately, again, we think root test. And that is the right thing. The right thing on the top one is the think root test. That is definitely the right thing. It's just that with these, things just don't always work out the way we want them to. So here, let's go with root test again. That's definitely the natural first choice. Let's see if it is more productive in this case. So the kth root, that means we're going to take the kth root of each of these factors inside here. So we're going to end up with 2 multiplied by 3 divided by k. And that limit as k goes to infinity is 0. So this one works out beautifully. This is what we like to see with the root test. So there we have our convergence. So just like the geometric series, now they call this rho instead of r, so they call that rho for the root test. So if rho is less than 1, we have convergence. Parallels the geometric series. Less than 1 converge, greater than 1 diverge. That's what we hope to see when we come across a summation that has a bunch of powers of k. We hope that it's going to be like the instantaneous kind of conclusion. That's what we want. That is what we like. That's often how the root test works. Root test is often super fast. 4 out of 5 times it's super fast. Okay. We got this really oddball looking thing. Remember that when we do our triage here of trying to figure out what to do, especially if something looks really unfamiliar, let's think divergence test first, at least think it. As k goes to infinity, do our terms go to 0?
No.
What is sine of 0?
0.
0.
Oh.
So yes. So divergence test is inconclusive, but we at least want to consider that. So as k is going to infinity, the inside of sine is going to 0, right? 1 over k to the 9th is going to 0. So then the limit of this is sine of 0. Sine of 0 is 0. So it's possible that there is convergence here. Feels like it's unlikely. Feels like they, but I don't know. We'll find out. Okay, so the next thing we might want to do is, it doesn't look, it's not one of our special series. We have our 4 special ones. It's definitely not geometric. It's not a P series. It's not an alternating series. It's not a telescoping series. It's not one of our 4. Ratio test makes no sense.
Integral.
We could try to integrate it, but integrating with a k to the with an x to the 9. Remember, if we're going to integrate, we'd probably need to use substitution, which means the derivative would have to be somewhere. The derivative of k to the 9 is not in there. So integral test feels like not a good way to go. Certainly ratio and root test are out. There's no factorial. There's no, like, taking the kth root of that just makes it look worse. The last thing on our list is the comparison test. And we did do the comparison test with a couple of oddball things. Like we had 1 over the natural log of k. You know, that's in a similar boat here where we compared this to 1 over k and we were able to show that this diverged. So this is kind of one of those oddball ones that maybe we should try a comparison. And the question is what to compare it to. And I want to show you something that, I want to show you a geometric view of something that is helpful as you go through these math courses. So let's just suppose that we're looking at an angle right there, and I'm going to draw this. And let's suppose the angle is theta. And if this is a unit circle, then this arc out here, let me use a different color for the arc. The arc is also theta. And on a unit circle, because you have the formula S is equal to R theta. And if you have a unit circle, 1 times theta, that's the multiplication. All right, so S and theta are the same. Isn't this vertical line right here sine of theta? Right? So what is this inequality? If we look at the inequality between these two, so theta in our case is 1 over k to the 9. So as theta is going to 0, isn't it true that theta is always bigger than sine theta? Right? That arc is longer than the straight line down. Right? You can see it visually. You can prove it with Calc 1, the derivative. If the derivative is negative, it's decreasing. You can create a decreasing type of thing if you move one of these to the other side. But you see it visually. You see, oh yeah, that theta is always bigger than sine theta. That arc is always more than that vertical distance. So that kind of gives us a hint for the comparison. So we're going to choose our b sub k. So we're thinking of this whole thing as theta. We're going to think of b sub k as that. That's theta. Let's see what happens. So B sub k, so this is a P series. P is 9, greater than 1, therefore convergence. Oh, okay, does that thing converge? Let's find out. So what we want to show is that the A sub k, which is this, we want to show that that's less than the B sub k, which converges. So that's what we want to show. Usually I put the generic one up top, which, why am I changing now? I don't know. So we want to show that A sub k is less than B sub k. So we want this to be true. And that is true. This is considered a fact that we should know from Calc 1. Just like we know that x is bigger than natural log of x. If we look at the graph of x and natural log of x, it's that same argument. We already know that. That's kind of an accepted fact. There's y equals x. There's y equals natural log of x. X is bigger than natural log of x. Same idea here. We can look visually at the picture, and this is theta. That's the arc. There's sine of theta. In this case, theta is on the inside. There's theta. This is going to be true. So this is true. Therefore, we actually get convergence. Even though it looks like we probably won't. It feels like the sine function sort of would create some wobbling that wouldn't allow it to go to 0 fast enough. But what happens is that the inside here goes to 0 so fast that the inside is going to go to 0 so fast that the sine function is not going to create enough oscillation for it to diverge. All right, there we go. Let's take a 10-minute break. And then we will wrap up this random section. Yeah, so first off, we see that doing the kth root makes a lot of sense. That we see the power of k on the outside. There's a couple of things we could do to clean it up first a little bit. Let's do one cleanup step. Let's get rid of that negative first because that just feels annoying right now. So let's do that. So we could rewrite it that way. And then let's go ahead and use the kth root. So that's rho equals the limit of the kth root of a sub k. And we don't have to worry about the absolute value here because everything's positive. So we'll end up with the limit. When we take the kth root of that, we end up with this. And this is our classic generalized E limit. We can do our fraction splitting. And when we do our fraction splitting, we end up with that. And what is that limit? E to the power of 10. So remember, we get e to the whatever this number is times whatever that number is. This has to be a plus here. Make sure that that's a plus. So if you had a minus right there, you would shove it into that numerator to the right and make that a plus. Okay, so root test, like the ratio test, like the geometric series, we compare this to 1. Is this bigger than 1 or less than 1? Bigger, therefore diverge. So that's also a classic root test that goes very nicely. Perfecto. Perfecto. Any questions on any of those? All right. Bye-bye, chapter 10. Now we get to the thing we've all been waiting for, infinite series of functions instead of infinite series of numbers. So these are going to be called power series. In other words, it's going to be a series of powers of x. It's really just a long polynomial where the power goes on and gets bigger and bigger and bigger forever. So a power series is a series of powers of x. And each one of these powers of x you can think as a function, right? X squared is a function, x cubed is a function, x to the fourth is a function. So it's really a series of functions. You're adding all these little functions together. Now for us, a power series, we're just dealing with powers of x. We're not dealing with sines and cosines or other functions that are in there. When you go on in a little bit, when you go up in math and up in physics, you will come across a special infinite series of functions called a Fourier series. And when you have a Fourier series, your terms are not going to be just powers of x. You're going to have sines and cosines inside of them, inside the terms. So why do we want to create such a thing is the first question. Like, are these important? Do they go on? Are we going to encounter them again? So here's sort of a brief overview. We know that polynomials are very easy to differentiate. They're very easy to integrate. Add power, divide by the new power, bring the power down, subtract 1. Like, really easy. Much easier than most of our other common functions like logs and exponentials and sines and cosines and inverse functions. What happens is that almost all of our common functions, most of them can be written as power series. Almost every function that you encounter can be written as this never-ending or infinite polynomial, which is going to be convenient in many ways. So that's the first thing, is that most functions, so let me give you an analogy. If you have the number line and you pick a number off the number line, what's the probability that it's rational versus irrational? What's it more likely to be, rational or irrational?
Irrational.
Irrational. 99% of the numbers on that number line are irrational. You pick off a number, the chances of it being rational are epsilon, tiny. But in everyday life, we use rational numbers all the time because they're just easier, right? The square root of 2s, the square root of 5s, the pi's, we don't see those that commonly, right? Those are more uncommon in everyday life. So even though there's many more irrationals, you're more likely to pick an irrational, but we still use rationals. Analogy. When you think of a cloud that has every possible function, so a function cloud, when you pull a function out of the function cloud, 99% of the time, it will not be a nice, neat, common function. 99% of the functions you pull out of the function cloud are going to be power series with random coefficients that will not simplify to common functions. So most of the functions we use are these common functions, these ones that are very nicely behaved. But most functions are not nicely behaved. Most functions are going to have this power series form where there's not enough pattern in the coefficients to create an e to the x, a sine x, a cosine x, inverse tangent x. So power series are super important because most functions are actually power series. There's only a handful that have a nice nickname, like sine x or cosine x. Like you think about the irrationals. If you pull off an irrational, there's only a few that we have nice names for. E to the pi, those kind of things. Pi, square root of 2, square root of 5. But there's many more irrationals that have no name to them. Right? You just imagine this mystery decimal expansion that has no pattern to it. Right? There's a bazillion irrational numbers that we have no name for. So it's the same type of thing. When you get into engineering, it turns out that most of our common functions can be written as infinite series of sines and cosines added together, which are is super convenient because if you have a smooth function, again, you can take its derivative and its integral. And in engineering, you deal a lot with electricity where you have these patterns that are functions that have gaps in them. They're step functions. And you can actually approximate a step function with an infinite series of sines and cosines. It'll look like a really tight wiggle going around the squares of the wave. And then you can do math on it. If you have a function that has sines and cosines, you can differentiate, you can integrate, you can do all the math stuff. And so after we get through power series, you will eventually encounter Fourier series where there's sines and cosines in there. So these things will come back to haunt you. So it's a good idea not to, like say, this is just a small little tidbit. You do need to understand series because they're super common throughout. So that's the motivation for making sure that you try to stay engaged with us. So we've got this infinite polynomial. This one is centered at the origin. This more generalized power series is centered at A. So we always think of a power series as having a center. Think of the center as something on, think about the x-axis. If you plug in x equals A, so you replace all these x's with A, don't all these terms just disappear if you plug in x equals A, right? Because you get A minus A, A minus A, A minus A. So at the center of your power series, you're going to have this constant value. So if you plug in x equals A, this is the constant value right here. This has no x in it. So a power series will reduce down to just its constant at the center. This one at the center is 0. If you plug in 0, everything disappears and you just have that constant. But when you're thinking of a power series, there's an infinite number of choices for the x. So a power series is actually an infinite collection of infinite series. There's an infinite series of numbers if you plug in x equals 1, if you plug in x equals 2, if you plug in x equals a half. Every x value that you plug in there, you get an infinite series like we've been doing in chapter 10. So there's an infinite number of choices for those x's. Now we know that series of numbers can either converge or diverge. So a natural question is, well, what are the x's that we can plug in that give us convergence? The ones that give us divergence are less important. We want to know what x's can we plug into this infinite polynomial and get convergence. And so that's, again, going to be our question. We want to know, well, when does this converge? In other words, what's the domain of that power series? The domain is the set of x's for which the function is defined. And when we think about a power series being defined, we mean, oh yeah, where does it converge? And so here are some examples. Oh, and let me just point out, so the beginning, the leading terms of a power series, that should remind you of S sub n. Right, so the sum of the first, this is a polynomial of degree n, so the first n plus 1 terms here, because we're counting from 0, that's just a polynomial. And then the terms just continue. So it becomes, we can call it an infinite polynomial or a never-ending polynomial, something like that. So here are two super common power series. The most common, the most important of all, is e to the x. And there's its expanded power series form, and there's its closed form, its summation notation. So that is e to the x. And its domain, in the context of power series, instead of domain, we use the word interval of convergence. And no matter what x value you plug in there, it will converge. And it converges to, like if you put a 2 in there, e squared, so 2.7 squared, will equal 1 plus 2 plus 4 over 2 factorial plus 8 over 3 factorial. It'll be exactly equal. So every single x value that you plug in, you will have convergence. And you can see all the regular stuff with e to the x. If you take the derivative of this, you get the same thing back. Derivative of 1 is 0. Derivative of x is 1. So you're right there. Derivative of this term, you get 2x over 2. The 2's cancel, you get x. Derivative of this term is that. The derivative of that term is that. So you get that you can see that the derivative of e to the x is e to the x.
I think we couldn't take the derivative of factorial.
This is a constant.
Oh, okay.
So we're not taking the derivative of x factorial. So the derivative of a constant times a function, that constant factors to the front. So when we differentiate this, we're just differentiating the 2x. This is just 3x squared, and the 3 factorial still sits below it, and then you can cancel. But yeah, we're not differentiating the factorial itself. The factorial is just a constant here. So there's e to the x. Here's natural log of x. So this one is centered at 0, and this one is centered at 1. So you can always see the center. It's kind of like those shifted polynomials that we dealt with back in college algebra and pre-calc. Like if you do the shifting of a quadratic. So the center is always the number that gives you zeros for everything except possibly the first term. So here the center is 0. You can see that at 0, everything cancels except the 1. Here the center is 1. When we plug in 1, we end up with 0. Which, notice, if you do plug in 1 on the left, natural log of 1 we know is 0. Natural log of 1 is 0, and you get it on the right also. So these infinite polynomials, aka power series, look like that. All right, so let's go back to Calc 1. And what we are going to do is sort of go down a journey to get to power series by going back to Calc 1 and starting with the best linear approximation to a function. So the best linear approximation to a function is the tangent line. And you may never have talked about the slope of a curve, but the slope of a curve is defined to be the slope of the corresponding tangent line. So the slope of this curve right here is whatever the slope of that tangent line is. We know that if a curve is smooth, there's unique tangent lines at each point. And so the slope of that tangent line will be called the slope of the curve. So slope, the slope of this curve will match the slope of that tangent line. To build the equation of this tangent line, we use the point slope formula, and we come up with the first order approximation for this curve up here. So p sub 1, in Calc 1, you just wrote that as y. We're going to write it as p because we're going to create a whole bunch of polynomials, and we're going to have the power of the polynomial reflected with the subscript. So the first order approximation is the tangent line. It's first order, so that's going to be a 1. That is the equation of the tangent line if you solve for y. You do your point slope formula. You have that point on the curve. The point on that curve is a comma f of a. Slope of it is f prime of a. And if you do the point slope formula and solve for y, and you call y p1, you get that. So there's the tangent line. Two important properties of the tangent line. It matches, the tangent line is the p, so its value at a matches the function at a. That's that point. So the tangent line and the function have the same y coordinate at x equals a. So the value of the function and the value of the tangent line match. That's an important key for a tangent line. And the other important feature is that the slopes match. The slope of the line is the same as the slope of the curve. So in other words, they have the same first derivative at a. So value and slope match. So that's what makes a tangent line. It is the line where the value and the slope match. So if we can create a linear approximation, we should be able to create a quadratic approximation. This should be even better. It should be a better approximation. So that's what we're going to do. So we're going to create the best quadratic approximation. And you can see that by generalizing our approximation curve a little bit, it's a lot better. This blue curve approximates this black curve way better than that tangent line. The tangent line's only good when you're really, very close to the point of tangency. So let's figure it out. Well, how can we create the best quadratic approximation, the best fitting parabola? Well, we have some conditions that have to be true. So first off, here is the tangent line, right there. So there's the tangent line. That's the best linear approximation. And this has to be part of the best quadratic approximation. It has to be. We want the value and the slope to match. And when we go to the best quadratic approximation, we also want the concavity to match. So in other words, here is value. Value is the 0th derivative. And then we want the first derivatives to match. So that one is called value. This one is called slope. And then we also want the concavity to match. So the best quadratic approximation is going to be one that satisfies all three of those. We certainly want the value to match. We certainly want the slope to match. And then we want the concavity to match. And so in order to maintain value and slope matching, we just are going to tack on to the already existing tangent line. We're going to say, hey, let's just add a quadratic component to this tangent line. There's our tangent line. Now let's add a quadratic piece. But that quadratic piece has to satisfy these things. Let's check. If we plug in an a for the x, then all of this vanishes and we get p sub 2 of a equals f of a. So if we plug in an a right there, this term will disappear like we want it to. We want the values to match. So p sub 2 of a is equal to f of a. Now let's go to the derivatives. So we want the derivative of we want the derivatives to match. So we want the derivative of p sub 2 to match the derivative of f. And then that's going to be our last term. Let's find out. So there's our general. There it is. There's our general p sub 2. So we're trying to figure out if we want the best quadratic approximation. Our goal right now is to say, well, what does this constant have to be? To create the best quadratic approximation that satisfies these three conditions, what does C2 have to be? So now let's go back to Calc 1. Let's take a derivative. So we said the values have to match, the slopes have to match, and the concavity has to match. Let's see. So I claim that this is the derivative. I also suspect that you're not all going to see that instantly. What is the derivative of f of a? 0. That's a constant. A is a constant. So A is the only variable is x. A is a constant. So the derivative of f of a is 0. It's gone. Now the derivative of this term. So the derivative of term 2 right there, this is the derivative of that. Do you see it? Well, f prime of a is a constant. You multiply it by x. So f prime of a times x. What's the derivative of f prime of a times x? It's f prime of a. Right? It's the coefficient of x. How about when you distribute the f prime of a to a? F prime of a is a constant. F prime of a times a is a constant, so its derivative is 0. So the derivative of this whole second term is just that. Now we take the derivative of our third term. Derivative of our third term is this. We use the power rule. The 2 comes down. We subtract 1 from the exponent, and then we multiply by the derivative of the base, which is just 1. So this is the first derivative of our p sub 2. Let's do it again. Let's take another derivative. Let's get down to the second derivative, because we want the function and the polynomial to have the same second derivative. What's the derivative of f prime of a? 0, because that's just a constant. Now we come over here and we imagine distributing. So if we take this 2c2, we distribute it to the x, we distribute it to the a. 2c2 times x, what's its derivative? 2c2. Right? If we have that, the derivative of a constant times x is the constant. The constant is 2c2. And 2c2 times a is a constant. Its derivative is 0. So this is the second derivative of the polynomial. All right, Well, we can solve for C2. That is what we've been looking for. We've been looking for what C2 has to be. And we are going to, this is our assumption. We want the second derivative of this polynomial to match the second derivative of the function. So if we're going to use that assumption, the second derivative of the polynomial is equal to the second derivative of the function. We have now built the C sub 2, and we now have the quadratic best fit. That is going to be the best fit for the quadratic. And you can start to see a pattern already. This term is f prime of a, first derivative, first power on x minus a. And then we do second derivative of a, second power on x minus a, but we divide by 2. So you can almost predict what the third term is going to be. It looks like the third term is going to be f triple prime of a divided by 3 times x minus a to the third. There is one tweak, though. There's one small misconception there, which let me show you real quick. It turns out that if you literally go out the same way that we just did for a second order, do the same thing for a third and a fourth order, it turns out that it's not just a 2 under that f double prime. It's actually going to be a 2 factorial. So we're going to see that the third term out is going to be f triple prime over 3 factorial. So we're going to see that this is always going to match, but that denominator is not just the k, like it looked like it was going to be just a k. It's actually going to turn into a k factorial when you go a couple terms out. You'll see it. But that's not where we're at yet. So we have this function. They give us a center, and they say, find the best linear approximation, the best quadratic approximation. All right. Well, when we come off, we can write our, if we write our best second order approximation, p sub 2 of x, well, let's write them both over here. So p sub 1 of x, that's the tangent line. That's f of a plus f prime of a times x minus a. That's your best linear approximation. That's your tangent line. That's what you spent weeks dealing with in Calc 1. To get our best quadratic approximation, all we have to do is take that tangent line and add a quadratic term. That's going to be that. So there's our best linear, and there's our best quadratic. So we need some information. We need the first derivative. We need the second derivative of our function. There's our function. So I'm going to write our function here, and I like to do this as if I'm building a table. So I start with the function, and we need to get down to its second derivative. So I'm going to write the function with a negative exponent because that's the easiest way to take derivatives repeatedly. So there is the function, there's its first derivative, there's its second derivative. And our form over here, we need the first and the second derivative and the function evaluated at a. So now my next column is going to be the evaluation at a for each of these 3 functions. Oops, second derivative. So we're going to evaluate the function at 1, and we get 1. Evaluate the derivative at 1, and we'll get negative 1. Evaluate the second derivative at 1, we'll get 2. Now we can build our 2 approximations. So p sub 1, it's a function, so we'll put in of x. That is 1, right there, f of 1, plus f prime of 1 is this negative 1, so that's a minus, times x minus a is 1. So there is p sub 1. You do not have to simplify these approximating polynomials. The only one that's going to simplify in any decent way is the first couple. So we usually don't simplify them at all. So there's P1. P sub 2 is going to be exactly P sub 1, but then we add the quadratic piece to it. So the quadratic piece says take the second derivative of f at 1, which is 2, divide it by 2, and then have x minus 1 to the 2. So this piece of it we will simplify. We can simplify this coefficient and make that 1. So there we go. This is our best linear approximation, aka Mr. Tangent Line. And there's our best quadratic approximation, Ms. Parabola. So this is the idea, and you're starting to see how what we are doing is bootstrapping our way through to build a power series. So this is the quadratic approximation. Then we can go to a cubic approximation, a quartic approximation, a quintic approximation, and then dot, 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 and you've got a power series. That's where we're going. We're not there yet, but that's where we're going. So let's try another one of these. So we've got our function, and we want to build these approximations for the function. Let me ask you a question. How do you think your calculator figures out e squared? You type your calculator, you put in e, you do the square. How does your calculator figure out sine of 1 radian? Power series is how all your technology computes function values. Right? Like there's no unit circle inside your calculator with a little wheel, like nothing like that. So it goes to the power series for whatever the function is, e to the x, sine of x, whatever it is, and it goes out far enough so that the accuracy will fit however big your window is. So if you're on a calculator with 10 digits, it will go out far enough so that it's exactly right out to 10 digits. So there's going to be a remainder formula that tells it that you're within 10 to the minus whatever it is, so that you can get accuracy to your screen. So you have been using power series most of your life. Anytime you're typing into a computer or a calculator doing math, it's using power series. Okay, so let's do another one of these. Let's build up the second order. So first off, we have our function. So start with the function, write it with the rational exponent, and then we're going to take our sequence of derivatives. And we are only going out to the second derivative because we just want the second order power series. Second order approximation. Power series go on forever. This approximation stops. Oh, there's a piece of the first one we didn't answer yet. We'll answer it in a second. So now we evaluate the function and its derivatives at the center. Center here is given to be 4. F prime of 4. You plug in a 4 right there, square root, so we get a fourth. Square root of 4 is 2, but it's in the denominator. F double prime of 4. So maybe we should look at this one more carefully. So this is 1 over, so we're going to have 4 to the 3 halves in the denominator. So F double prime of 4. So negative 1/4 times 1 over. All right, so square root of 4 is 2. 2 cubed is 8. So we get negative 1 over 32. All right, so now we can build our polynomials. So P sub 1 of x is going to be f of a, 2, plus f prime of a multiplied by x minus a.
I thought f of a was, oh wait, oh, sorry.
So a in this case is 4, so f of a is f of 4. And if you do this systematically with this table approach, you'll also sort of get some kinesthetic, like this is always where you start there, and then you're going to add this one, and then you're going to add the next one. And here we have to be a little careful. So remember up here, we have to divide by the 2. So we took that one and then divided by 2. So this all has to be divided by 2 now, multiplied by x minus 4 quantity squared. So let's just, I did, that's going to be for p sub 2.
Okay, that's.
Yeah, sorry, let's move that down there. So p sub 2 will be p sub 1 plus that second order term. So let's simplify p sub 2 a little bit. Let's not distribute anything. Let's just simplify that coefficient a little bit. So minus 1 over 64. So there is our second order approximation. All right, so we didn't answer the approximation question. So let's do that. Let's come up to that one. Well, first off, does everyone understand the terms here? So here's going to be our first one. Any question on how we generated the terms? So there are 2 approximations.
I have one question. Should
Yeah.
it be 1 over 32 all over? Oh wait, no.
1 over 32 all divided by 2.
Flipped
Yeah.
it the wrong way. No.
Yeah, flip the right way. All right, so the question here says, let's use these 2 approximations to evaluate 1 over 1.05. Let's approximate 1 over 1.05. Okay, so first, when we look at our function, we have to figure out where x is. So x is right there. So this is x, right? Everyone agree? So if we want to find an approximation for, let's use this color. So P1 of 1.05, that's x. So P1 of that is going to be 1 minus 1.05 minus 1. So we subtract off 1 and we get 0.05. Then we subtract that from that, so we get 0.95. So that is going to be our approximation. Now let's do it for this one. So P sub 2 of 1.05 will be 1 minus, we can do this subtraction in our head, 1.05 minus 1, that's 0.05. So that's our tangent line approximation. And then here we have plus, we're going to do 1.05 minus 1, which is 0.05, but then we have to square it. So 0.05 squared. So can someone type that into your calculator and get what that's going to be equal to?
0.025, right? Wait, no.
So when we square that, we're going to get, 0.0025. But is it going to be just this? Is that it? Somebody type it in just to make sure that's
I think
it.
so.
And then if we type into our calculator, let's get the value by just typing in. This is obviously one we could do differently. We could do 1 divided by 1.05, and this is actually equal to, if we write out some decimals here, 2, 3, 8, 0, etc. We can see that as we go further out with our higher order approximations, we get, gets better and better. But we didn't have to go that far. We just went out to the second order, and we're already good to the third decimal place. So a lot of these approximations can converge quite quickly. Let's take a look at this one in terms of the approximations. So our center is 4. Okay, so we built that. And you might start to see a pattern here that you choose your center in a way that is going to be close to where you're trying to approximate. So here, when we're looking at this, we know the closest number to 3.9 that is a perfect square is 4. So we're trying to pick a number that's close to the number we're approximating at. So let's check this one. So we have p sub 1 of 3.9. So in this case, the x is everything underneath the square root. So that's x right there, 3.9. So p1 of 3.9 is going to be 2 plus a fourth. And then 3.9 minus 4 is negative 1/10, negative 0.1. And so this is going to be 2 minus 1/40. That's going to be 80/40 minus 1/40 is 79/40. So that is going to be our approximation. We could write it as a decimal also, it doesn't really matter. And then, same idea down here, so p sub 2 of 3.9. We're going to have 2 plus a fourth times 3.9 minus 4 is negative 1/10. And then minus 1 over 64, again, negative 1/10, quantity squared. So this is going to be 79 over 40 minus 1 over, that's 100, so whatever this is going to end up being. Whatever that will be. 79 divided by 40 minus 1 divided by 6,400. So decimally, this would be 1.97484, etc. This one, if we wrote it as a decimal, would be... Writing it as a decimal will allow us to see a little bit more carefully how close it is. So square root of 3.9 is going to be square root, where are you there? So this is going to be 1.97484, etc. Okay, so the first one is good to three places, 3 sig figs, 2 decimal places. The next one we get out to 97484. Oh, it's already good to 5 decimal places, just going out to the second order approximation. All right, any questions on building these approximations? Everyone okay with the P1, P2? All right, so tangent line, quadratic. These things are called Taylor polynomials. So a Taylor polynomial is what you call this, basically the sum of the first n plus 1 terms. So the best linear approximation is p sub 1. Notice it has 2 terms, not 1, because there's a constant and then the power of 1. The quadratic approximation has 3 terms, it's p sub 2. And so these are, in general, we refer to them as Taylor polynomials. And you can create an nth order Taylor polynomial by going all the way out to the nth power. So the nth order Taylor polynomial, which is p sub n, will have n plus 1 terms. And like I mentioned earlier, we thought our coefficient had a 2 in the denominator, which it does, but it's really a 2 factorial. If you go to the third term, you're going to see that the denominator is 6, which is 3 factorial, and etc. If you were to go through the process we already went through, you would see that these denominators end up being factorials. And so here is an image. The curve, our function, is the exponential function. First order polynomial, second order polynomial, third order polynomial, and of course they're getting more and more, they're approximating the function better and better and better on a wider interval. Let's see, I wish I was logged in here. I don't think I have the ability to log in fast. I think I'd have to think too much. So I built a thing in Desmos that will kind of give you a good visual for this, but, oh, I'm logged in. So let's go here. Taylor polynomials. Is it in alphabetical order? I doubt it. Taylor polynomials. So let's pick a function. What function is this? This is e. Oh, how convenient. There's e to the x. Okay, so there's the best linear approximation right there. And as we go further and further out, there's the best quadratic, there's the best cubic, there's the best quartic, there's the best quintic, and you can see what's happening. Right, the function, the polynomial, the Taylor polynomial is getting better and better. And as we keep going further and further out, the right side matches very quickly. The left side is going to start matching. It does match exactly, but it takes a lot longer. But that's what it's going to do. It's going to start wrapping around the curve. Let's try the sine function. So there's the sine function. And let's get back to here. So there's the sine function, and here is the one I want to use. I don't want to use that one. That one was for E. Okay, so there's the best linear approximation to the sine function. Notice that we match at 0. There is no quadratic approximation because the quadratic term is going to end up having a 0 coefficient. So this is actually a cubic here. And so we're going to have, all of these are going to be odd powers, right? Because the tail is going opposite directions. So we're going to have the same idea, right? As we go further and further out, it matches perfectly right around the center really fast. But it is going to actually match the entire function as n goes to infinity. So that's what's happening. And this is why we want to pick a center. If we're trying to approximate, somewhere out in La La Land, we want to pick a center that's close to where we're approximating so we don't have to go far out in the series to get a good read. So let's look at this one. This one's going to be weird. So there's arctan. Now this is super weird. So we go out, and what we notice is that we only have an interval of convergence that's real tight around here. It's going to turn out that that interval of convergence is from minus pi over 2 to pi over 2. We'll talk about why that is. But so this power series is only good for a smaller region. And then here's another one. This is 1 over 1 minus x. That's the function. There is the corresponding power series, and this one's going to be super weird. So, okay, it's linear, quadratic, cubic. And what we're going to notice is that it's only going to match from -1 to 1. Doesn't this function have a vertical asymptote at 1? So this is one of those really inexplicable things that happen. So this function, if I center the power series at 0, the distance to the nearest asymptote is 1. And somehow, this derivative process knows that it can't converge any further than 1, and so it doesn't let convergence happen any further than 1 on the other side. So if you have a function and there's a vertical asymptote, the radius of the interval is going to be the distance to that asymptote, the closest asymptote. And somehow the process of doing these repeated derivatives to get these coefficients will build the function in such a way that you can't have convergence like offset. The center of convergence is here, or the center of the power series is here. Convergence is always on a symmetric interval around that center. It feels really inexplicable. It's like, okay, yeah, this side's going to match all the way out as soon as we get as close to 1 as we want. But this side, it feels like, can it approximate out there beyond? And it can't. It's always going to be symmetric. The interval of convergence will always be symmetric about the center of the series, which is, very, very weird, because it feels like it should be possible to create an approximation that continues to match this direction, but it doesn't. Okay, so the last couple of power series had intervals of convergence that weren't the whole real line. They had a narrower interval. So this one wants us to go out a little deeper. They want us to go all the way out to p sub 5. So what that tells us is that, okay, we're going to start with our function, and we need to go all the way down to which derivative? Fifth. And I'm going to start using y's instead, because writing it's going to be quicker. So we have y, and then we have to go y prime. Yeah, when you start having to write a ton of these down, you want to use the easiest possible method. So derivative of e to the negative x, the derivative of that, we have to go all the way down to the 5th derivative. And when we start to get to derivatives that are higher than 3, then we put a little index in parentheses. All right, so there we go. The function, and it's down to its 5th derivative. All right, now we have to evaluate that function and its derivatives at the center. Center they've given us is 0. So y of 0, oh, that's just 1. Y prime of 0, negative 1. Ooh, this looks pretty decent. So we just get 1 or negative 1 all the way down. There we go. So p sub 5, I'm going to write p sub 5, because you've seen now that p sub 2 includes p sub 1, so we can just write p sub 5 and do a little clever labeling instead of writing out 5, writing out this polynomial repeatedly. So p sub 5 starts with p sub 1. So it's going to be 1, right there, top right corner is where we start. So it's going to be 1 minus. Now the center is 0, so we just have an x minus 0. We'll just write it as x. So 1 minus x raised to the 1st power. And then we're going to go plus 1. Now this is the 2nd order term, so we're going to have to divide by 2, or more generally 2 factorial. And then it's going to be x minus 0, which we'll just write as x, squared. So here is p sub 1 right here. Here is p sub 2 right there. So we can just write p sub 5, and the others are pieces of it. So be a little clever. So now to get to p sub 3, we've got to add this -1, so it's going to be -1. What will the denominator be?
3 factorial.
Yes, 3 factorial. And then x to the 3. So there is p sub 3. To get to p sub 4, we just add another 1 divided by 4 factorial, x to the 4th. There's p sub 4. To get to p sub 5, then you see the pattern. So that is p sub 5, and p sub 4 would be right there. So that is the 5th order Taylor polynomial for e to the -x. So this is not a series yet. It's just a finite, it's a polynomial. It's a 5th order polynomial, but you can see where this is going. You can see that if we go plus ... then we will have the corresponding power series. But right now we're still just dealing with polynomials, approximating polynomials. These polynomials are approximating that function. So we'll do one more here. Well, why don't you all try this one? So same thing, go down to the 5th order polynomial. Do it the same way I did it there. Just draw one polynomial instead of writing 5 separate ones, or 4. Oh, I guess here they just want you to write 2 separate ones. Everyone get the grunt work done? Function and 5 of its derivatives all evaluated at pi over 6. So we just have to remember the pattern and build it systematically. It's not too crazy. The pattern, you'll see, will become repeatable as you do a few of these. So we start with f of a, and then it's minus 1/2 times x minus pi divided by 6. So that is the tangent line right there.
Would that be P1 then?
Yep, that's P1.
Okay, you wrote P5.
Yeah, we're not done.
Oh, okay.
We're going to keep going. So then minus root 3 over 2. But we're going to have to divide by 2 factorial here, so I'm going to put a 2 factorial in there. And then x minus pi divided by 6 quantity squared. So that's p sub 2. And so here's where we first start seeing this extra factor there. So now we have p sub 2. P sub 3, we're going to add the next one, so that's plus 1/2. But here we have to divide by 3 factorial, x minus pi divided by 6 cubed. So now we have that extra 3 factorial, but it always matches the power on the x. And let's write the next 2 terms down here. So then we have plus the square root of 3 over 2 with a 4 factorial, x minus pi over 6 raised to the 4th power. So that's all p sub 4. And then minus 1/2 and we're going to have to drop in a 5 factorial for that one. And again, simplifying, totally unnecessary. You lose, the patterns all get obscured if you start multiplying things out together. So we don't need to simplify anything here. Just leave it like that. So that is p sub 5. So this polynomial approximates the cosine function centered at pi over 6. So if we look at the x-axis at pi over 6, it's going to be very tight right around pi over 6, but getting closer and closer as we go out. And if we keep adding more terms, it's going to end up matching it exactly. So this is how we would approximate for a number that's close to pi over 6. So the center of the power series, or the center of the Taylor polynomial, is close to where we're trying to make an approximation. All right, well, let's stop. Let's stop now. We have a test coming up. Like 2 weeks from today. Our final test before our final exam. I can't believe we just finished week 11. Yeah, 2 weeks from today. So get going on the Chapter 10 worksheet. Make sure you get ahead of the game on that. And I will see y'all on Tuesday. Have a good weekend.
You as well.
And we'll enjoy some spring weather. Don't be too distracted.
I'm gonna rewatch this lecture like 5 times. Towards the end there, I was like,
What's
towards the end,
happening?
I was starting to get the procedural stuff, but when you first started introducing chapter 11, I'm like,